Okay, so good morning, everybody. I'm not sure how many people are actually there. At the moment, I see 0 viewers, which doesn't sound so encouraging. However, I really hope that students will basically join soon. First of all, let me tell you that this is an experiment, meaning that it's actually the first time in this course that we do a class live streaming on YouTube. I hope you will appreciate it. I know it's not so common, but well, being this course about multimedia networking and as streaming live is one of our classes of applications, I think it actually makes perfect sense to test the technology also in the lecturing process. Now, before starting the actual class, I would like to do a little bit of housekeeping. So, first of all, I sent out yesterday a message on the Moodle for basically how to set up meetings with myself and Nicola. The reason is that, well, we were just getting overwhelmed by different requests, and we just would like to have, a standard process so that this helps us in making sure that we can set up quickly a meeting with you, making sure that we will actually be able to follow you in your project activities, okay? So, I mean, don't get scared, you will get used to it. I think it's actually a very good methodology, and I actually suggested to use it also with other professors, or if you need for your professional career to set up meetings or whatever. Okay, something more. Some students came up to myself and Nicola stating that basically, well, they didn't like the project that they received, so they wanted to propose a new project. And we said, no, it's not possible. I mean, game over. You had the time to propose projects, you didn't do it, fine, you just stick to what you received. Or, of course, if you manage, you can swap the project with other groups. That is perfectly fine with us. Just let us know. I think the deadline is actually tomorrow afternoon. Okay, something more. I also sent out a message through Moodle. You will get users. I send out a lot of messages to students about ICT Days. So for the ones who didn't do their bachelor here in Trento, ICT Days, it's really a very big event for the university, in particular for the Department of Computer Science and Telecommunications, where you are located. And I warmly encourage you to do at least the job placement. It's actually a very good opportunity for you to really see how a job interview looks like, not by studying the theory, but by basically, well, going there, presenting your CV, talking to companies, and something which I really recommend to students is to try to land an internship for the summer. I know you probably would prefer to go to Ibiza with your girlfriend or boyfriend, but still, I really tell you, it's actually a very good opportunity for your career. What you learn by spending 2 or 3 months in a company, it's actually much worth than well, what you can get spending 3 weeks at Ibiza. Okay, whatever. Oh yes, there is also the hackathon that I actually co-organize. That's not for everybody, but if somebody, if some of you really like coding and you would like to play with real-world data about energy consumption and the production, it can actually be a good opportunity. And of course, there is this small incentives of the 500 euros prize for the winning team. What else? Yes, Monday next week, bring a notepad and a pen, because we will do a projects planning lab. So basically, you will be working in team. I will guide you through an example of how to develop a project plan, because next week on Tuesday is the deadline for the first assignment. So basically, well, I just wanted to provide you a little bit of hands-on practice on how to draw a project plan in reality. Okay, so I think we're ready to start. There is a Q&A application, which is actually on the left-hand side. So if there is any question you would like to ask, I mean, you just type it, okay, and I will answer to it as soon as I get it. Okay, now let's start. Let me see if I managed to get this working. Okay, so the topic of today is actually quality of multimedia. So what you have seen so far in this course was really kind of the basics of TCP IP networking and a little bit of network measurements. Probably most of you actually had already seen these things in your bachelor courses, but still I believed it was good to make sure that you are all at the same level. So today we are actually starting another big topic, which is about multimedia content itself. And actually what we will discuss today is how to assess the quality of a multimedia content. And of course, this is key because as a network engineer, what typically you have to do is to optimize the way the network can support multimedia applications. But the usage of the term optimization underpins some notion of what is best, what is actually good, and what is actually the way to improve things, right? And this is what we call quality. And as we will see, when it comes to multimedia content, and I will mostly refer today to videos, but this applies also to audio or any other type of multimedia applications, really, it's actually not so easy to define what is meant by quality. Actually, there are a lot of different notions because, for example, quality might mean no noise. I mean, if you have taken courses in digital communications or wireless communications, well, you know that the problem is really the noise typically, and what you would like to make sure is that you get rid of the noise. If you have taken some computer vision or image processing courses, well, there is also this issue about fidelity with respect to the original. For example, when doing audio or video compression, something you will see extensively in the second part of this course, the one given by Nicola, you will see that the point there is that you have an originally high quality content, and you would like to basically, well, compress it without losing a lot. This is the concept of fidelity. The transformed image or video should be as close as possible to the original. Then you might actually think of something which has no visual artifacts. So, for example, you are not really, I don't know, applying a filter to an image or things like this. And this is kind of, you know, kind of objective notions. I mean, it's something which happens to the content, but actually you can think of quality of multimedia also in terms of something pleasant, something which is actually nice to see and to watch. And actually all these notions are good ones. So there is not a single one-size-fits-all notion of quality in multimedia applications. But there are different viewpoints, but depending on the specific case, you need to combine. And that is actually where you also need to be a little bit creative, because you need to understand, based on the specific peculiarity and requirements of the application, which notion of quality is actually the best one to use. Okay, in general, I will give you now a little bit of classification of quality concepts and quality measures. Typically, there are two ways of looking at it in terms of quality. One is to check if the content reflects the original video or audio or whatever. So the point is that you have something which is the original multimedia content, typically what you have at the transmitter. You send it over a network which also includes compression, packetization, whatever really. You get something at the receiver, and you want to check, to compare whether what was received is actually close in a given metric space to what was transmitted. And this, of course, accounts for things such as consistency and manipulation. Another viewpoint is actually to check if the content has a positive impact on the user. So whether the user actually liked the content and whether he finds the content appealing. These two notions are both relevant. They actually pursue different goals, and depending on the specific application, you might actually want to use one or the other. Okay, now, if we need to build a taxonomy of quality metrics for multimedia, there are two big categories. One is what we call objective quality metrics or quality measures. What it means, objectives? It means that it is based on data that can be measured, so hard data, numbers, right? And then you have a formula which basically put all these measurements together and provide you a compound index of quality. Typically, the advantages of these are that it's pretty easy to compute them. You need to do some measure to get some KPIs, key performance indicators. We already mentioned a few of them, like delay, jitter, bandwidth, packet loss. But of course, this is somehow just an approximation of how users perceive video. And we will see some examples later on what this actually means. There are also subjective measures. And by subjective measures, I mean actually situations in which you ask people to rate the quality of a given multimedia content. So it's not automated. It's not a software script that is run somewhere in the cloud. It's about showing videos to people or audio or whatever, asking them to rate the quality of the content and making some statistical analysis of the outcome of this survey. The big advantage is that, of course, this reflects the actual user perception. Well, you're actually asking the users directly, so it's not automated, so it's actually real. The shortcoming is that it is complex. It is cumbersome, and often it is very, very expensive. So keep in mind throughout the class of today, and well, actually for the rest of the course, these two categories, objective quality metrics and subjective quality metrics. Okay, now, historically, the concept of quality in multimedia was associated to compression of signal. Why this? Because typically multimedia content is by nature analog, and when you need to digitalize it, to send it over some digital communication network, you need to perform a number of steps, sampling, quantization, and compression. And one of the things that people spent a long time was devising good compression schemes, where the good means something which can actually provide high quality results. For us, we will still reuse much of the terminology and methods which has been introduced by people in signal processing and signal compression. But for us, it's not about the compression. For us, we need a measure of quality which accounts for whatever may happen between the transmitter and the receiver. Keep in mind the scheme that we saw in the first class. We basically have one transmission entity which has a multimedia content, and it wants to transmit this content to another party at the other end of the network. So basically, for us, the notion of quality should account actually for the network, which again is an IP network with all the limitations that you now know in terms of best effort service, potentially out of order packets, packet errors, packet going lost, and so on and so forth. Okay, two notions that are really important and that map nicely to this dichotomy that we saw before between subjective and objective quality measures. The first one is quality of experience, which is a subjective measure of a customer's experiences with a service. So basically, you use a service, for example, you watch a video, and when I ask you, are you happy with it, yes or no? If you use Skype, from time to time, Skype asks you to rate the quality of the communication. I think it has a star rating system from 1 to 5, if I recall. So it basically asks you to rate the quality of experience. If you were happy with the service, this video conferencing real-time service that Skype provided to you for free. Another notion, which is somehow related, but is not the same, is that of quality of service. Quality of service is an objective measure of the quality guaranteed by the service provider. So think, for example, when you sign a contract for an ADSL network, typically you get what are called SLA, service level agreements. You sign up a contract for a 7 megabit per second ADSL 2+, which means that you have a theoretically maximal bandwidth of 7 megabit per second in download, and I think it's 384 kilobit per second in upload. And if you check the contract, what's written in font 8 in the contract, typically you have some guarantees. So you have some minimal bandwidth which is guaranteed to you by the service provider. These two notions are equally important, but there is also a lot of friction between the two concepts. Why? Because quality of experience is subjective, first of all, and is what the user cares about. You care about the quality of your experience. If you use Skype, you basically want that the voice doesn't break and so on and so forth. You don't care about jitter or bandwidth or throughput. These are technicalities that are hidden from you as a user. On the opposite, if you are a service provider or a network provider, what you reason about is in terms of quality of service, is about objective measures, something which can actually be measured experimentally, but you can say it's 3 or 5, okay, and 5 is better than 3 or whatever, and is basically describing what you provide to the users. And of course, if I reason in terms of quality of service, let's say bandwidth, delay, and jitter, but for whatever reason something goes wrong and you have a bad quality of experience, then we have a problem, because me, service provider, I am convinced that I'm giving you a very good service, but you as a user are not happy at all with the quality of experience. So there is a lot of tension between these two, as written here on the slide. The users reason in terms of quality of experience, and service providers, and in particular network providers, reason in terms of quality of service. And of course, the question, is there a way to bridge these two aspects? Is there a formula, ideally, that links quality of service, which is objective and measurable, to quality of experience, how a user perceives the service? The answer is unfortunately negative. There is no golden standard for linking quality of service, which can be measured, to quality of experience, whose measurements is much more difficult. There are some methods that go in this direction, but they present limitations. So in many cases, if you are a service provider and you need to understand if the users are happy with the service, there is nothing more you can do than basically resorting to subjective measures, which are complex, are expensive, but in many cases are the only way to know really what the user perceives about the quality of the service you provide. Okay, now I will introduce you a number of different schemes that have been proposed for measuring the quality of multimedia applications. Why I'm doing it? Not because you need to remember all the details, but because I think it's important for you to understand what people are doing, how they are measuring these things, and also to get some grasp of the difficulties in really bridging these two words, quality of service, quality of experience, subjective measures versus objective measures. And we will start with the oldest quality measure introduced, which is the MOS, Mean Opinion Score. It is a subjective measurement, so actually working with real people, okay? And it has been used for decades in telephony to basically understand how humans perceived the quality of the audio signal. How was it organized? Well, actually, first of all, this is something which is standardized. It is standardized by ITU, International Telecommunication Unions. We actually found this acronym as a standardization body for the X25 packet switching standard in one of the previous classes. It is standardized as an ITU tier recommendation, number P800, and it basically contains instructions on how to set up tests with users. It's actually quite funny to read it in details because, well, it's actually really full of details. Here I am just, I put an excerpt from the actual standard. So it actually states that the talker should be seated in a quiet room with volume between 30 and 120 cubic meters and a reverberation time less than 500 milliseconds, but preferably in the range 200 to 300 milliseconds. And the room noise must be below 30 dBA with no dominant peaks in the spectrum and so on and so forth. Okay, so it's actually fully detailed, but basically how it was run, you put users in a quiet room, you let them listen to some words, to some conversation, and actually the standard specifies also which sentences should be used, and you ask them to rate the quality of the sound as they perceive it from 1 to 5. So basically, 1, it's really bad. So it's actually very annoying impairment, okay? And 5 is excellent. So basically, there is no impairment which can be perceived by the human here. What you saw on the slide is actually the scored card that is given to the people who take part in MOS tests. So this is subjective. It requires to test things with a number of users. But as you're asking users about how they perceive the quality, well, this is actually reflecting the actual user perception, the actual quality of experience. Okay, yes, something important, of course, the standard specifies a methodology for choosing users. You cannot choose them at random, but you should have something which is representative of the whole population in terms of age, in terms of gender, in terms of education level, and so on and so forth. And that's something which I found it really weird, is that actually there are some suitable sentences to be used. So it cannot be just whatever type of audio, but there are some sentences like, you will have to be very quiet, there was nothing to be seen, they worshipped wooden idols, which is really ridiculous to me, but anyway, I want a minute with the inspector and didn't need any money. So this is just to give an idea of how basically people have been running subjective quality measures. And if you wonder whether this is still in use, well, the mean opinion score for telephony is not really longer in use, but actually the methodology is used extensively for video coding analysis of video compression. Okay, some examples that relate actually to audio compression. You probably have seen in some digital communication courses the G711 standard, the PCM, pulse code modulation, which is the first digital telephony standard that was introduced. You basically take audio, you sample it at a frequency of 8 kilohertz, 8,000 samples per second, and you apply an 8-bit logarithmic quantization. So you end up with an audio stream which has a bandwidth of 64 kilobit per second. And this, experimentally, has been tested. It has a mean opinion score of 4.1. But if I go back to what I had before, it means it's somewhere, it's actually a little bit more than good. Not excellent, but still good. So basically, you have some impairments that are perceptible, but not annoying. Of course, people working on digital communications then develop new standard. And in particular here, I put the data for the G729, which is the one used in GSM mobile telephony. I don't actually remember what this acronym CSACELP stands for. But anyway, this doesn't really mind. But what you should notice is that G729 has a bandwidth of 8 kilobit per second. So it's actually one order of magnitude less than G711. And it has a mean opinion score of 3.92. So it's actually very close to G711 in terms of perceived quality by user, yet it consumes much less bandwidth. Okay, so this is just to give you an idea of how MOS has been used extensively in the design of audio compression schemes. Now, is there a way of linking some objective measures to the mean opinion score? Yes. Actually, people at ITU, people from the telco world, in particular from vendors and mobile networks operators, spent a lot of time trying to come up with something that links the mean opinion score with something that can be measured in practice. Just because the mean opinion score, it's really expensive to measure. And you see, if it's about data compression, well, you put people in one room, you let them listen to some sentences, and you ask them to rate it, and that's okay. But if you need to perform mean opinion score type of tests over a network, then of course you should account for all possible sender-receiver combination, which is just not feasible. So people felt they needed to have something which could be computed automatically based on network measurements, and they came up with what is known as the E model, which is again standardized as ITU-T recommendation G107. It is something which provides a prediction of the expected voice quality. So this kind of, it's also called synthetic mean opinion score for a complete end-to-end telephone connection. And it accounts for impairments due to, well, the fact that basically you're using low bitrate coding devices, one-way delay, jitter, noise, echo, and so on and so forth. The figure that you see here, it looks really old-fashioned. It actually is quite old-fashioned, and it's actually taken from the official ITU specifications. This defines what you see in bold are all the parameters that should be measured. And basically, if you have all these parameters, there is one formula which tells you what is the expected mean opinion score. Or better, there is one formula which gives you the R factor. What is the R factor? The R factor is well, an intermediate step, and I will tell in a while how this relates to the mean opinion score. But let's look first at the formula. So you have the first term, R subscript 0, which accounts for the basic signal-to-noise ratio, received speech level relative to circuit and acoustic noise. You have a term, IS, which accounts for impairments, including the fact that the speech level might be too loud, that the side tone might be not optimal, to the fact that you are quantizing, so you have quantization noise, and so on and so forth. You have another term, ID, which accounts for delay, including jitter, and echo effects. Plus, you have an IEF term, which stands for Effective Equipment Impairment Factor, which represents what is basically due to coding, compression, and to packet losses of random distributions. So far it's pretty basically standard. I mean, I think it's quite easy to understand it. So you have a term which accounts for signal to noise ratio. That's a basic of any digital communication schemes. You have something which accounts for the fact that, well, you have quantization and so on and so forth. You have something which accounts for delay and echo. You have something which accounts for problems with the end equipment, so basically coding and whatever. But you have one factor, A, which is really important, which is called the advantage factor. What it means? It means actually that it was noticed by running mean opinion score tests, but unconsciously users are not perceiving some quality impairments if there is an advantage. What do I mean? One thing that people tested, for example, was to give them a cellular phone and a fixed phone. And they were giving audio which was exactly the same. Yet people provided a higher rating for the audio coming out of the cellular phone, even if it was exactly the same as of the fixed phone. Why this? Because people felt unconsciously again, but of course with a cellular phone you can go around, you can move, what you cannot do with a fixed phone. And unconsciously, this in the human brain created some notion of higher accepted level of impairments, so that basically people ended up perceiving this as higher quality noise. So even in this formula, which is again an objective quality measure, you have these factors which account for the way human perception works. So you basically end up, if you put all the data in this formula with the transmission rating factor R, and then there is a formula which maps the value of R to a mean opinion score. This is the formula, and if you look and if you plot it, it looks like this. So on the x-axis you have the R factor, and on the y-axis you have the mean opinion score. Something you should notice here is that this formula doesn't cover the full range. It doesn't go from 1 to 5, but it actually stops at 4.5. You can actually see it also from the last line in this slide here. So why was it done this way? Well, just because the E-model was developed by engineers that needed to dimension a system. And when you dimension a system, you want to dimension it for the worst case. So you typically prefer to be a bit cautious and to kind of, keep on the safe side. So by basically making sure that what was measured by the E-model was not going up to 5, they were, in a sense, keeping a little bit of slack, which helped them in developing systems that performed well and were perceived by the users as good quality ones. So this was actually about audio, because as I said, the mean opinion score was really introduced for telephony, for fixed telephony actually. However, the mean opinion score is actually used also for videos. The procedure that is followed is basically the same. You need to select the videos for testing. You need to find a sufficient number of subjects for the evaluation. And of course, you should choose them in such a way that they are a representative sample of the population. You ask them to assign a score from 1 to 5, and then you collect the scores and compute the average. Actually, this was a project that we gave, I believe, 2 years ago. So we actually asked some of your colleagues to go out, select videos, select users, and run this with, I think, at least 200 users. And it was actually quite interesting to see the results and how the mean opinion score correlates with factors related, for example, to age and education. Okay, so what are the critical points if you want to do mean opinion score for multimedia contents? First is the choice of the users, different age, cultural background, and so on and so forth. The second one is the number of users. Of course, the higher, the better. The choice of the score range. Range 1 to 5 is very used in the US and in Anglo-Saxon countries. In Italy and other countries, we typically work with a range from 1 to 10, which is, however, very different because in a range from 1 to 5, 3 is actually good, but in a range from 1 to 10, 6 is considered barely acceptable. So actually, there are a lot of issues which are non-trivial here. And something very important is whether the test should be blind versus non-blind. What it means. If it is blind, it means that basically I'm going to show you a distorted video and I ask you to rate the quality. Non-blind means that first I show you the full high-definition video, and then I show you the distorted video and I ask you to rate the distorted video. And actually, the fact that you have seen the original high-definition video changes a lot your perception of the quality of a distorted video. And of course, well, even if you decide to go for a non-blind test, which means you also show the original video, you might want to do it. You first show the original and then the distorted, or you show first the distorted and then the original, or you show them side by side. I mean, there are a lot of things that need to be decided. And of course, this is extremely time consuming because assume you have even a 10 minutes video and you do it non-blind, which means that basically you need to multiply it by 2. It's already 20 minutes video per user. You might want to show to a given user multiple videos to basically understand whether this user has some bias. Let's say 10 videos, makes it already for 200 minutes. If you show it to, let's say, 100 people, which is the bare minimum, this accounts already for 20,000 minutes of time spent just by letting people watching videos. Plus, of course, there is the rating plus the analysis. So it's really time consuming. Okay, so before moving to objective video evaluation, I'm going to stop the screen sharing. And now it's your time if there is any question you would like to ask me. Wow, it seems everybody's shy. I cannot point at you now because, okay, I see there are 30 viewers, but I don't know who you are, of course. So I will give you 1 more minute to think about questions related to this subjective quality evaluation of videos, and then we move to objective measures. Okay, there is a first question. Isn't fidelity and visual artifact related to each other and almost the same thing? No, that's actually a good question. I will show you in a while some examples of images where you will see that fidelity measured in terms of a pixel by pixel difference doesn't actually account for visual artifact. So just wait some 5 minutes and you will basically see some nice graphical examples that explain you the difference between these two concepts. Okay, no more questions, it seems. 1, 2, 3. Okay, so let's move again to the second part, which is about objective performance evaluation, objective quality estimation of videos, sorry. So what they are mathematical models that approximate the results of subjective quality assessments. But they are based on criteria and metrics that can be measured objectively and automatically evaluated by a computer program. So objective methods are classified based on the availability of the original video signal, which typically should be of high quality, non-distorted, and not compressed. So this is objective because it's based on measured data, and you have one formula that gives you one number which should estimate the perceived quality. Into objective video evaluation metrics, we can define 3 broad classes, depending on whether, in the assessment of the quality, they make use of the original content or not. We talk about full reference algorithm. So full reference algorithms are algorithms that use both the original and the distorted video for basically comparing them, kind of pixel by pixel, really, and performing a difference analysis. We have at the opposite end of the spectrum no reference algorithms. So algorithms that use only the degraded signal, what we get at the receiver, for the quality estimation. And we have something in between, which are reduced reference algorithms, which are algorithms that don't use the full original video, but extract some parameters, typically some statistics, average brightness or these things, at the sending site, and they use these parameters and the degraded video signal for assessing the perceived quality at the receiver side. So just to make sure that you get the basic points, okay? So there are 2 ways of measuring quality: subjective versus objective. Subjective is mean opinion score. Objective, we further subdivide them into 3 categories: full reference, reduced reference, and no reference, okay? So let's see some example. Perceptual evaluation of video quality is a standardized objective measurements methodology to score the picture quality of a video. It is again standardized by ITUT as recommendation J247. It's based on a 5-point synthetic MOS, so it actually gives you as output something which is in the range 1 to 5. It's an end-to-end quality testing method, so it accounts for whatever might happen into the network from the source to the destination. And it is a full reference testing, meaning that basically it needs to have access also to the original video for basically comparison purposes. PEVQ is used quite extensively in the multimedia delivery industry. There are some commercial tools that provide it. It's actually quite complex to run this test, but if you browse online, you can actually find the formulas. Something which is more traditional and widely used, in particular in university courses, is the peak signal-to-noise ratio. Well, you know what is the signal-to-noise ratio? It's just the ratio between the maximum power of a signal and the noise that affects it. And what you basically do it, you compute this signal-to-noise ratio by summing up over all single pixels in the image. It is full reference, so you basically take, for each video, you take each single frame of a video and you compare pixel to pixel what is the difference. And you basically have this formula. I also introduced here the mean square error, which is something which is used extensively in statistics. And the peak signal-to-noise ratio can be written according to this formula. So it's basically 20 times the log base 10 of the maximum intensity of the signal minus 10 log base 10 of the mean square error. So this is full reference. It's very simple. It just compares pixel by pixel. As we will see later on, the peak signal-to-noise ratio is a measure of fidelity, okay? Because it really tells you how close is the image in the video to what was originally sent. Yet, as we will see, it doesn't account for visual artifacts. That is actually why people introduced another measure, which is called the structural similarity index. It is again a full reference metric, but this was designed to account for visual impairments. There is a formula actually here. So what you basically do is that you divide each image of the video into small squares. For each squares, you take the mean, indicated by mu, and the variance and the correlation between points on the XY axis. And you basically have this formula, you have these values, C1 and C2, which are parameters. There is a lot of literature on how to set them. But what I want to show you now is an example. So let me try to zoom in. Here you see a picture of Albert Einstein, okay? And this picture, the original one is the one that you see on the top left. So it has mean square error equals to 0, so maximum peak signal-to-noise ratio, and it has a structural similarity index of 1. So it's actually, well, the original one, the top one. Then we can add some different types of distortion. So, for example, let's look at the pictures in the first row. Here, what was done was to add some noise, but basically introduces the same fidelity. The mean square error is the same. It's 306 for the second, 309 for the third, 309 for the fourth. But the structural similarity index is quite different. So even if these three pictures are the same from a point of view of fidelity, pixel by pixel difference, the way we perceive it is actually very different. In particular, the second one, we perceived it's just barely distorted. But if we look at the fourth one and we compare it with the first one, then we see it is actually really different. Even worse is actually the second row. Here again, the first three pictures have the same mean square error, around 300 and something. So it's basically the same as the second one. But as you can see, it's really very, very of bad quality. At least this is how the human brain perceives them. It's really heavily distorted. And this is actually represented by the fact that the structural similarity index is decreasing from 730 down to 641. Okay, so similar also for the last one. In the last ones, there has been a number of distortion added, so that basically the mean square error changes quite a lot, but the structural similarity index is almost the same. And if you look at the figures, the pictures in the last row, you can barely notice the difference. So in a sense, whereas the peak signal-to-noise ratio and the mean square error, because they are related in a linear way, are good at accounting for fidelity, this is not a good way of describing how the quality of something is perceived by the human brain. That is why people introduce the structural similarity index, which is again objective and full reference, and which provides a better grasp of how people perceive the quality of image. Okay, so here I have another example. Is example of a picture of a baby with a pretty strange haircut, whatever. And here what the people did was to introduce some distortions, okay? And distortions in image processing, you will see actually much more about this in Nicola's part, can be characterized as non-structural distortion and structural distortions. Both distortions can change the mean square error, the peak signal-to-noise ratio, but non-structural distortions don't change the structural similarity index. For example, we can change the luminance, we can change the contrast, we can apply some gamma distortion, we can spatially shift the picture, and still, our brain has difficulties in really seeing this as very different from the original one. So for us, this is good quality. But if we apply some structural distortion, noise contamination, blurring, JPEG blocking, wavelet ringing, and so on and so forth, we actually perceive it as heavily distorted and hence of low quality. Okay? So basically, this gives an idea of the fact that not all noise is the same. Even on one single image, the type of noise that can be measured by the peak signal-to-noise ratio cannot really tell me much about how I perceive the quality of an image. Okay, now let's move one step back. We saw in one of the first classes that we have 4 network-level key performance indicators: the throughput, the packet loss rate, the one-way delay, and the jitter. And we have spent this one lecture basically using tools for understanding how to measure them, okay? We have seen the use of TCP dump, we have seen the use of ping for measuring one-way delay, we have mentioned the use of GPS clocks for measuring one-way delay. We have discussed a bit about traffic generator. It's a pity we didn't manage to do it live. Probably we will try to do it in one of the next classes. But basically, you should have a clear picture that these are the 4 things that as a network engineer, you can measure on a network. So, one of the things that network engineers came up with is another quality metric, which is objective, which is no reference. So both peak signal-to-noise ratio and the other ones that we saw were full reference. This is non-reference, so it doesn't need to know anything about the original video. But this is just a set of measures that are used to monitor the quality of a delivered video. This is something, again, which was standardized, but not by ITU, but by IETF, the Internet Engineering Task Force, as request for comment number 4445. As anything that comes out of IETF, it is very simple. It is pretty much thought to be used, designed for being easily implemented. And in this case, it refers only to network impairments. So to things that network engineers know very well how to measure. It has a quite limited relationship to quality of experience because it's really simple, but it is still very useful for dimensioning purposes. This is what any network engineer uses for understanding how good is the network at supporting multimedia flows. So the media delivery index, it's actually represented as a pair of two measures, the delay factor and the media loss rate. So now I want to show you how these are actually defined and measured. Okay, here I have a picture which is meant to just refresh a little bit your brain in terms of what we need, what we mean by jitter. What the plot represents is the number of total packets received over time. And we assume here that the network is sending packets at a constant bit rate. So let's say every 100 milliseconds, one packet is pushed from the source into the network. If we have no jitter, which means that the delay is the same for all packets, we end up with the blue line. So it is actually a straight line, which means that the number of packets received over time grows linearly, modulo granularity of the packets, of course, with respect to time. If, as in any real operational network, we have jitter, so the delay varies over time, we have something which looks like the red one. So it basically, it is a line, but it changes shape as time moves by. So for example, at the beginning, we have actually a long delay. When the delay shortens down, so basically the line becomes steeper. Then again, we have a very long, a period in which we have very long delays. Then again, it changes and we have a very fast transmission of packets and so on and so forth. Now, one point that we will see on Tuesday next week is that basically when we have jitter, we need to compensate for jitter. Because if packets were generated by sampling with a constant period, a multimedia signal, at the receiver end, in order to play the content out, I need to basically reconstruct this timing so that I am basically playing out these packets with the same sampling period with which they were sent by the transmitter. So basically, I need to compensate for it. And actually, I need to have a way of understanding how much jitter is in the network. The delay factor does exactly this. It is expressed in milliseconds, but it has nothing to do with a one-way delay, okay? In the MDI, Media Delivery Index, the delay factor is not about the one-way delay, but it's about the jitter. Formally, it is defined as the size of a buffer needed to eliminate the jitter over the media rate. This will become clear, I guess, next week. But basically, the idea is that in order to compensate for the jitter, what you should do is to have a buffer at the receiver. So that basically packets get into the buffer at whatever rate at which packets arrive, and you drain, you take packets out of the buffer at a constant pace, where this constant pace is the same pace at which the packets were delivered by the sender. So that basically you effectively compensate for the variation in delay. So what you do, you basically measure the number of received bytes and the number of drained bytes. You compute this delta, and you compute it over a number of time intervals. typical durations of 5 seconds, and you basically compute the maximum of delta minus the minimum of delta over the media rate, which is basically the rate at which the stream was encoded. And this formula gives you the delay factor. There are some rule of thumbs. So basically, values between 9 to 50 milliseconds are actually acceptable in most applications. 50 milliseconds is a bit limit for multimedia interactive applications, but it's still good for streaming stored content or streaming live content, what we are basically doing right now. The second factor of the MDI is the media loss rate, which is the number of media packets lost over a certain time interval. Usually here you measure it over 1 second. This is really simple. It's the difference between the packets expected and the packets received divided by the interval time in seconds. Also here there are some rule of thumbs in terms of what are acceptable values. For video over IP, what we're doing now, live streaming, 0.004 is okay. Similar for video on demand. If you want to do high definition TV over IP or 3D internet streaming, you need to go one order of magnitude down to 0.0005. What are the problems with MDI? Well, MDI, it's really, really simple. I mean, you just measure things at the receiver. You just count packets, basically, because if you check, this is all about received bytes, drained bytes, media rate, packets expected, packets received, interval time. So it's very simple to use. But of course, well, simplicity has a cost. And the cost is that it is not a very good measure of the perceived quality. In particular, there is one problem, but as you will see in Nicola's part, not all the frames are equal. So when we transmit a video, not all the frames in the video have the same importance. There are some frames that are more important than others. Depends on the coding schemes, but is basically like that for all the coding schemes that are used in practice as of today. And second, it does not consider the effect of noise. As we have seen before with the peak signal-to-noise ratios and the SSIM, not all the noise is equal. The human visual systems is very complex to model. So MDI is good because it's simple, but it has a number of limitations. Okay, in the next class on Tuesday next week, Monday, we have this project planning lab. What we will do is to understand how to map quality to IP network features. And in particular, we will see some basic algorithms, basic methods that people have developed, and methods that are actually used in all multimedia applications for basically concealing or accounting for network level impairments. In particular, we will be discussing about playout buffering, erasure codes, so packet level forward error correction, and interleaving. And then after ICT dates, we will discuss a little bit about architectures for quality of service support over IP networks. Okay, so I am done with the slides. We have now some 5–10 minutes for questions. So please, the floor is yours. On the left-hand side of the screen, you have a box, a blue one, with written Q&A. You click on it, you type a question, and I will see it. Okay? Wow, I cannot believe there are no questions. I cannot believe everything was clear. Come on. Okay, it looks like really there are no questions, so I will give you the last 20 seconds, and then we can consider the class over. I hope I hope it worked. I hope it was kind of handy for you also to watch me remotely from Barcelona, actually. So I will distribute a questionnaire because I want to collect some feedback. As I said, this was an experiment for us to do it, this lecture in video conference. But I want to make sure that you kind of liked it so that we can understand whether to repeat it or not. So given that there are no questions, thank you very much for having attended this video. I see that basically we have had around 30 people watching the video, so about half of the class. Please tell your colleagues that this is actually being recorded, so they can actually watch it on the same YouTube link that was shared yesterday. And see you Monday next week. For the ones that I am going to meet tomorrow and on Friday, we will have the meetings in CreateNet, which is Via della Cascata. It's 100 meters north of the Dizzy. You work in the direction north, there is the roundabout. You take the way down, 50 meters on your right, you will see there are some reddish buildings. You enter and you ask for myself at the reception, and I will come pick you up. Okay, thank you very much. Have a nice day. Bye-bye.